Namaste, Namaste everyone. Welcome to second PUC physics class. We were discussing about the AC circuit containing resistors, inductors and capacitors. Namaste. Individually we have seen and what will be the power dissipated in resistive, inductive and capacitive circuit. Now we will connect all the three in series and how do they react and which will lead and which will lag behind in an AC circuit. That AC circuit containing resistor, inductor and capacitor in series, and we call it as series resonance circuit. It is an electrical resonance. You will understand what is electrical resonance. Okay, series resonance circuit. Okay, so you have to connect an AC source with a resistor, a capacitor and an inductor in series. So R be the resistance of the resistor, C be the capacitance of the capacitor, L be the self-inductance of the inductor, and V is equal to Vm sin omega T be the alternating voltage that is applied, sinusoidally varying voltage, and Vm is the peak value of EMF, and V is the instantaneous value at any instant of time t, right? If you substitute t, you will get the voltage value at that instant, instantaneous value, and omega is angular frequency, that is 2 pi by t or 2 pi nu. You know this, the angular frequency with which armature will rotate. Armature will rotate with the uniform angular velocity omega. Okay, so that is applied in all together. Now, how do they behave? Now, I will rub this. Okay, this is needed. V is equal to Vm sin omega t. In all the previous cases, what did we do is we tried to get the equation for current. And suppose the current was also having I is equal to Im sin omega t equation, we concluded that current and voltages are in phase. That is in resistor. But in capacitor, we found that I is equal to Im sin omega t plus pi by 2. Current was leading. In inductor, I is equal to Im sin omega t minus pi by 2. Current was lagging. Voltage was leading. So we got different results. What may be the result? Shall we discuss it and shall we guess what may be the result here? So you may say that current is in phase with the voltage. But we can't conclude because there is resistor. And a resistor says current should be in phase with the voltage. Whenever current is maximum, voltage should also be maximum. When current is 0, voltage should be 0. And when current is in a certain value, voltage should also be a corresponding value so that they are in phase. But capacitor says current should lead. Current should become maximum in the beginning itself. Whereas inductor says no, voltage should lead and voltage should be maximum in the beginning and then the current should increase. By that time voltage should decrease. Now who will win this in this fighting? And who will win, that depends on finally the frequency, that is angular frequency omega of the source. So source decides which leads what, whether current leads voltage, whether voltage leads current, or whether current and voltages are in phase, and how much amount of current should flow in the circuit. Everything is decided by frequency of AC. So the behavior of this circuit finally depends on the frequency, the number of cycles repeated by the AC in 1 second. How many cycles you get? You can have different sources of different frequencies. You see, suppose you purchase a DC battery, variable DC battery, you will get a knob in the DC battery which can change the amplitude of the voltage. You can change that DC battery if it is a variable one. You can, suppose the maximum voltage is 10 volt, you can turn that knob and you can set it to 3 volt, 4 volt, 5 volt, 6 volt, and any value of voltage between 0 and 10. If you get an AC source, you will have two knobs in that, two variable knobs. One can vary the amplitude of the AC. You can change that AC of peak to peak value 10 volt. You can change that AC of peak to peak value 5 volt, peak to peak value 2 volt. So you can change the peak to peak value. That is what you call amplitude of AC. So you can make in an alternating voltage source, you have one arrangement, and that is usually called oscillator. Oscillator produces different AC voltages or AC alternating currents. So you can change the peak to peak value, right? You can make the voltage to vary from plus 10 to minus 10, right? Or you can change the amplitude from plus 5 to minus 5 like this, right, without changing the frequency. Of course it should be like this. Yeah, you can change the amplitude to vary from plus 3 to minus 3. You can change it to plus 7 to not like this, it should yeah, this is plus 10 to minus 10 and plus 7 to minus 7, but number of cycles repeated in 1 second is same. You say you can make it to change from plus 3 to minus 3 like this. And there is one more arrangement in an alternating source. You can change the number of cycles repeated, keeping the peak value the same. How? It is like this. Suppose the peak value of the EMF is plus 10 to minus 10. 10 volt is the peak value. Keeping the same peak value, you can change the number of cycles repeated in 1 second. You can change only the number of cycles. How? Now this produces 1 cycle per second, say. It's very low frequency. You can make more number of cycles to repeat in 1 second, but peak value is same. Can you understand? You can increase the number of cycles repeated. This is high frequency. The number of cycles repeated in 1 second is more, but peak value is same. So you can change the frequency. So the number of cycles repeated in 1 second keep on increasing, you are going on increasing the frequency. You have such an arrangement in an alternating source. We call it as an oscillator. So if you have such an oscillator, connect it here, which can give you the different frequencies. Whatever is the peak value, enough for us. Whether it is from 10 volt to minus 10, 100 to minus 10, minus 100, minus 50 to plus 50, whatever be the peak value, don't worry about it, because that is not the factor which is very important for us now. The factor which is very important for us now is frequency. Number of cycles repeated in 1 second. This is low frequency, only 1 cycle per second, say. And this is high frequency, more number of cycles per second, and this is very high frequency like this. So an oscillator can give you 500 hertz frequency, 30 hertz frequency, 50 hertz, 10 hertz, and it can even produce AC signals of 1000 hertz, 10,000 hertz, 50,000 hertz. That means 50,000 cycles per second. Whatever the AC that we use in our day-to-day life, that is KPTCL AC, it is 50 hertz per cycle. What do you mean by 50 hertz per cycle? Its RMS value is almost 220 volt, and it goes from 0 to the peak value and 0 minus peak value 0. This is called 1 cycle, and such cycles are repeated 50 times in a second. That is what we get in our home appliance sources. Sorry, in our home the electricity that we use in our house supplied by the KPTCL, that varies 50 times in a second, 50 cycles repeated in a second. That cannot be varied because it is a fixed AC with peak value and RMS value, and we don't change the number of cycles. But for these purposes, when we do some experiment, we can use some sources which can change the number of cycles repeated in a second. That decides the whole activity in the circuit. It is very surprising. It is not the current that you supply, amount of amplitude of current that you supply. So you can change the amplitude also, but it is not that one which controls the circuit. It is the frequency, number of cycles repeated, which controls the circuit. How? You see, now first we will go step by step. In this circuit, we will try to find out what is the total voltage across inductor, capacitor and resistor. You know, suppose you connect 3 resistances in series like this. This also looks very similar to that. You can draw this circuit like this. This is the AC source. AC source is represented like this, and if you connect a resistor, an inductor and a capacitor like this, very similar. You may see this type of circuit also in some of the books, because they are all in series. This is just designed like this, that's all. And you can put all the components like this. So this is also possible. Now if you connect 3 resistances in series like this, across a DC source. You have studied this. When three resistors of resistances R1, R2, R3 are connected in series, how do you write the total voltage? If V1 is the voltage across the first resistor, V2 is the voltage across the second resistor, and V3 is the voltage across the third resistor, total voltage supplied V must be equal to V1 plus V2 plus V3. Here there is nothing problem involved because all the voltages are in phase. That means when the current in the circuit is highest, definitely voltage across resistor will be its highest value, and V1, V2, V3 will be having their own highest value. When the current in the circuit decreases, voltage across the first resistor decreases as well as second as well as on the third. Because in a DC circuit, V equal to IR holds good, R is a constant. Whenever V is more, I is also more, right? V is equal to IR. Total R is a constant, R1, R2, R3. We are not changing the resistances. When I is more, V is more, they are in phase. So no problem across resistor. You can simply add the voltages. You need not worry about the phasors. In what direction, which leads, which lags, nothing is involved. Current is in phase with the voltage. There is no phase difference here. But when you come to here, this AC circuit, shall we add the voltages? Okay, I will rub this. This is not needed. This is what we do in DC circuits. Now, an AC circuit contains resistor, inductor and capacitor. Suppose this is the total voltage. Shall I use some chalks? This is the total voltage across RL and C. And if this is the voltage across VR, say it is the RMS value of voltage across resistor, and if this is the RMS voltage across inductor, and this is the RMS voltage across capacitor. If these three are the voltages across the resistor, inductor and capacitor, now shall I write the total voltage supplied as voltage across resistor, voltage across inductor plus voltage across capacitor? Can I write like this? No. This is wrong. You can't write the total voltage like this as if you write V1 plus V2 plus V3 across three resistors. That is not possible in this case. Why? Because you know that current flowing through all the three components are same. There is no problem in that. You can, you need not assume it. It is 100% sure because you know that all the components are in series. Whatever current flows through a resistor should flow through the inductor, and the same current should flow through the capacitor. Whenever the components are in series, current is same. You are very sure about it. You ask resistor, what amount of current is flowing through you? It says some ampere. Sir, at this moment it is so much ampere. At the next moment it will change. In the same moment, inductor will say, yes, sir, same amount of current through me too. And what about C? I am also experiencing the same current, sir, at the same moment. Okay, current is same, but voltages are different. Why? When current through the resistor is highest, you know, voltage across the resistor is also highest. But what about across inductor and capacitor? They are not highest, they are zeros. So when the current reaches the peak value, voltage across resistor and capacitor, they are at the zero values, because current in a resistor, current through the inductor and capacitor, when they reach the highest value, voltage across them will be zero values, because in an inductor and capacitor, current and voltages have a phase difference of 90 degrees, maybe leading or lagging, whatever it is, they have a phase difference of 90 degrees. They will never be maximum together. They don't attain the maximum value together and zero value together and minus maximum together in inductor and capacitor. They will always have a phase difference of 90 degrees. So now, how can I add the voltages then? If I separately find out the voltage across the inductor and separately across capacitor and separately across the resistor, you can't do that. Even if it is an AC circuit, if all the three components were resistors, I would have added, no problem at all. If all the three components were resistors instead of inductor and capacitor, I would have calculated the voltage across the first resistor as VR1, VR2 and VR3. I would have added this. But here it is impossible. They are not in phase. In phase values can be added, but values which are in different phases cannot be added. Simply I can give you an example. We have studied in interference, right? When two light waves of different that phase, when they superpose and on a screen, do we add the amplitudes of the two waves always? No. Amplitudes can be added only when they are in phase. That means if two waves fall in phase at a point, then the amplitudes can be added. The resultant amplitude is A plus B. You know that formula, R is equal to root of A square plus B square plus 2AB cos theta, resultant amplitude formula. That gives A plus B answer only when cos phi is cos 0, that is 1. We get A plus B. And if they are in opposite phase like this, if one wave is like this and another wave, light wave is like this, if they are falling in opposite phase means cos 180. Now you have to subtract the amplitudes A minus B, correct? So you can't add them directly. So now phase difference between voltages and currents decide how do you move to find out the total voltage. That is our aim now. Find out the total voltage across RLC, that is this V. That V is nothing but what the voltage is, source is supplied, right? Our source supplies the voltage. So source supplies an voltage of V at any instant of time t, that is given by Vm sin omega t. At that instant, VR be the voltage across R, VL be the voltage across L, and Vc be the voltage across C. And now what to do for V? Now we will take the help of current. This is very easy. This looks very horrible. Sir, what to do now? We can't add the voltages because they are not in phase. You can't add the voltage across R and L and C simultaneously. If suppose they are in phase, we might have added. If they are out of phase, opposite phase, we might have subtracted. And now what to do? Of course, it is very easy factor because current comes to our help. Why? Current flowing through all the resistors are, all the components are same. R, L, C. All experience the same current. Take current as reference. In some components, current and voltages may be in phase. In another component, current and voltages may be having phase difference of 90 degrees. Now current helps you to compare everything. Okay, we will take the help of phasor diagram now. I will draw the phasor diagram. Of course, in the examination, it is just a 1 minute job. Just write the phasor diagram, just derive it. Finished. But here I may take a long time because you have to have a very clear idea about what is that phasor and what is the why do we draw it like this, and what we are going to find out it now. It is the total voltage that we are finding it out. And now till this what I have explained, you have come to a conclusion that you can't add the voltages as if add the numbers. Suppose the supplied voltage is at a moment is 10 volt, and if the voltage across this is some 2 volt, 3 volt, something like that, you can't add them and you won't get 10 volt. We will have numerical values and we will prove that it is not the simple addition. It is a phasor addition actually. So you will come to know about this, right? Okay. Now, right. I will get the help of phasors now. I will draw a quadrant system like this. And I will write the phasors. Okay, yes, like this. Of course, we are going to draw this many times, but now you take a pen and paper and keep on drawing whatever I say, right? That is very important. If you don't have pen and paper, just run and bring a paper and pen and be ready with this. Now, you study one by one. Okay, here I have to draw actually. This is the voltage across R. Sir, whatever I have written here, VR, maybe RMS value, okay? If this is RMS, then everything is RMS. If I am writing the full voltage as RMS value, then all these values are RMS. If I am writing this as peak value, all the voltages are peak values. Okay, so voltage across C is VC, voltage across L is VL. Okay, and now you can write it as, suppose VR, if you are going to write what is VR numerically, right, magnitude of voltage, then it should be I into R. What is I? RMS value of current. VR, RMS value. If I is the peak value, then this is the peak value of voltage. What about VL? You know that Ohm's law. Voltage is equal to current into resistance. But inductor, current into reactance, because we call that particular opposition given by the inductor to the flow of AC as reactance. So what is the reactance of inductor? I into XL. XL is the reactance. What is the reactance offered by the capacitor? So voltage across the capacitor is same current through the capacitor, because all are in series. It is a reactance, I into XC, correct? Where XL is equal to omega L, that is 2 pi nu L, and XC is equal to 1 by omega C, that is 1 by 2 pi nu C. These are the inductive and capacitive reactances. Okay. Now we will take the help of current. We will write the position of current in the phasor diagram at a particular instant. And you know that when that current flows through the resistor, it produces a similar voltage which is in phase. Because you know, in a resistor, when current reaches highest value, voltage produced will also be the highest value. They reach highest values, zero values, negative values together. They are in phase. Resistor doesn't provide any phase difference for current and voltage. Both will be simultaneously maximum, simultaneously zero. So, if I write the phasor for current and voltage across resistor, if I represent the voltage across resistor here, current through the resistor will be the same position, right? So, they must be in the same condition, right? So, I is a common thing for all the components now. But across resistor, voltage and current are in phase. So, voltage across the resistor and current are in phase, so I can represent both the phasors in the same direction. Now take the help of current. For the same current, when it flows through the inductor, voltage leads, isn't it? By how much angle? By 90 degrees. So, when the current flows through the inductor, same current flows through the inductor, it produces a voltage which leads. That means by the time the current becomes maximum, voltage is zero. When by the time voltage is highest, current is zero. And the voltage will be highest in the beginning itself. That's why we say in an inductor, voltage leads, right? In an inductor, voltage leads. And in a capacitor, current leads, right? You know this. Okay. Then where do we apply, or where do we show the phasor of the voltage across resistor, across inductor? The phasor of the voltage across inductor should be somewhere here, because from this current, forget about the voltage across resistor, from this current it should lead by 90 degrees. So this is voltage across resistor, VR. VL. Voltage across inductor, that one. Same current flows through the capacitor. Now you ask the capacitor, where is the voltage across you, capacitor? Now capacitor says, sir, my voltage has to reach to the maximum afterwards. When current is highest through me, voltage is zero. And as the current falls to zero, voltage becomes maximum. And current leads. If current has to lead, same current, right? Same current through the capacitor. If current has to lead the voltage across capacitor, voltage must lag behind. So voltage across the capacitor comes here. Hope you have understood. This is 90 degrees. Right? Hope you have understood this phasor diagram. Understanding this phasor diagram is very, very important. If you have understood this, everything has been finished. Only mathematical calculations, mathematical derivations, those are the only things you have to take care of. Nothing else. The physics is over behind this. And now onwards, only mathematics. Hope you have followed this, right? Take the help of current. Current and voltage across resistor are in phase. So put them in the same direction. But voltage across the inductor leads the current. So put the voltage across inductor, because you know that this is the positive direction in which we turn, right? And leading, this is leading direction, that is what we show. So voltage leads. What about voltage across the capacitor? Same current flows through the capacitor. Now current should lead, voltage should lag. So like this. Now, what was our aim? What did we start actually? We connected resistor, inductor, capacitor all together in series, and we put them in series, connected a variable source, that is alternating, sinusoidally varying alternating voltage, V is equal to Vm sin omega t. We are trying to find out the total voltage applied across all these things. At any instant we want to find it out. The total voltage in terms of individual voltages across each component. We came to know that it is not the sum of all the voltages, because all the voltages are not in phase. That means voltage across when one component is maximum, voltage across another component may not be maximum. That is the difference, right? When voltage across one component is maximum at a particular time, it may not be maximum in another component. Its maximum voltage may be some other value, but they may not occur at the same time, because they have a phase difference. So, right. For example, when you study about your some people who have lived long back, say for freedom fighters of India, you just see the photo of Mahatma Gandhi and see the photo of Balagangadhar Tilak, and you see the photo of Sardar Vallabhbhai Patel. You see all old age photos, right? We feel that all of them were living together, and of course, and all of them were of same age. But no, they have a phase difference. Why? Because Bal Gangadhar Tilak was an old man even before Gandhiji, right? And Gandhiji became old later, and like this, one by one became old. But we see the photos together, but they have a phase difference. So you can't treat that all of them became old together in the same time. No, it's not so. So there is a difference. Similarly here, voltage across R, voltage across L, and voltage across C, you can't add them at a time. The reason is, I don't know whether my example is proper or not. When you can't add them simultaneously. Suppose the voltage across the resistor maximum value is 5 volt, and voltage across inductor maximum value is 10 volt. So voltage across capacitor maximum value is 7 volt. You can't write 5 plus 10 plus 7 because they don't go to maximum value together. That is the problem. They have a phase difference. When voltage across inductor is maximum, you see the phasor now? When the voltage across the inductor is maximum, voltage across the capacitor is minus maximum. And resistor is in a different, resistor is producing voltage in a different direction. So you can't add them as if you add numbers. You have to take the phasor diagram help. So now we'll move on. Of course, we are ready with all the voltages. Now you have to add them as if you add vectors, right? So if three vectors are acting, if three forces are acting at a point on an object, and two forces like this, where should I, if this is an object, two forces like this, 5 Newton and 3 Newton, and this is 2 Newton, say. Okay, 5, 3, okay, this is 5 should be shown by a long line. Say this is 2 Newton. What do you do for finding the resultant? Usually what we will do, if there are three forces, we reduce them to 2 first. Sir, how do you reduce the three forces into 2 forces? Very simple. If they are in the same direction, add them, because if the two vectors are in the same direction, cos theta becomes cos 0, 1. The whole equation reduces to root of a plus b whole square, a plus b. If they are in the opposite direction, cos 180 is minus 1. The whole equation reduces to root of a minus b whole square, a minus b. So if there are such forces, reduce them first. Same direction forces, simply add them. Opposite direction forces, simply subtract them. If they are in the perpendicular direction, apply the Pythagoras theorem, or root of a square plus b square, because cos 90 is 0. Can't we do it like this here? These three vectors are in the opposite direction. 5 Newton is stronger and 3 Newton is weaker, and 5 minus 3 can be done because they are exactly in opposite direction. One by one we will solve it. You need not take all the three forces together. One by one you can solve it. So 5 minus 3, that is 2, will come here, because you know if there are two teams in a tug of war, one team is stronger putting 5 Newton force, another team is a little bit weaker, 3 Newton force. Finally the rope will move in the direction of the stronger force with a force of 5 minus 3, that is 2 Newton. Okay, now the finally remaining two forces are this one and this one. The resultant of 5 and 3, that is 2, and this one 2. Find out the resultant by applying parallelogram law of forces. Root of 2 square plus 2 square plus 2 into 2 into cos 2ab cos 90. Cos 90 will be 0. So only root of 2 square plus 2 square. Finished. Similarly, you have to do it here. The voltage across L and voltage across C are exactly in opposite phase. They have a phase difference of 180 degrees. Sir, what do you mean by phase difference of 180 degrees? Remember, if peak value of current is flowing through all the three components, you know that voltage across L will be leading and voltage across C will be lagging. If one leads by 90, another lags by 90, then there will be a phase difference of 180 degrees. They come in the opposite direction. The meaning of this is, if the peak value of voltage across L is plus 5 volt, peak value of voltage across capacitor will be minus something volt. When this is plus, this will be minus. So the simply meaning like this, if this is plus minus, then this is minus plus. They produce a voltage which are 180 degree out of phase. What you see when you walk, your hands are 180 degree out of phase. One hand goes forward, another hand moves backward. So they have 180 degree out of phase difference. So why can't you subtract them, right? If you have voltages like this, you have applied KVL. It is like this. Suppose you have a resistor like this and another resistor like this. It is a part of a circuit, right? I imagine this is a part of circuit, and if the voltage here is plus minus and minus plus, if this is 3 volt, this is minus 2 volt, then totally, or you can imagine two batteries. That is best example. If you can imagine two batteries, like this, one like this, another like this. Suppose this is 3 volt and this is say some 7 volt. This is minus 7, this is plus 3, plus minus minus plus. So total you can write that is equal to minus 4. VL minus VC or VC minus VL. So these two vectors can be reduced into one. Now remember, don't forget what we are doing now. We are finding the resultant voltage. That's what we are doing. Now a question arises. Shall we go for VL minus VC or VC minus VL? Here starts the actual physics. Sir, it is VC minus VL. Why? Because this looks longer, this looks shorter. That is what I have drawn. This may not be longer. I can draw this longer. I have a chalk and I have a board. I can draw this one longer and this one shorter. It is my wish. Then it is VL minus VC. That we have to conclude. Which is a larger amount of voltage? VC magnitude wise, whether it is the voltage across the capacitor larger one or voltage across inductor larger one. Once you subtract it, then you can find out the resultant voltage between across the resistor as well as these two. Now voltage across resistor, voltage across inductor, among them which is the stronger? That is decided by, again come back now, that is decided by frequency. Because I will prove it like this, just simple chain like arrangement it is. Sir, VL is greater or VC is greater? Voltage across L is greater or voltage across C is greater? Voltage across L or C is greater or how much is decided by the product I into XL, I into XC, isn't it? Voltage across L and voltage across C, who is greater among these two? It is decided by I into XL or I into XC. I is common for both because they are in series. That means voltage across L and C, which is greater among them, is decided by XL or XC. Which is greater, XL or XC? XL or XC is greater whether it is decided by 2 pi nu L and 2 pi nu C, and finally nu is controlling them, because even though nu is same, one gets nu in the numerator, another gets nu in the denominator. Now suppose you are at very low frequencies. What do you mean by very low frequency? The number of cycles of AC repeated per second is very less. Then what happens? If nu is less, then XL is much greater than XC. Why? Reason? When nu is very low, suppose 2 hours, 3 hours, 4 hours, this is directly proportional to nu and this is inversely proportional to nu. And when nu is very less, XL is for low frequencies, XL is lesser than XC. Now, XL is lesser than XC. Now you have to go for, if XL is lesser than XC, VL is lesser than VC, this diagram holds good. If frequency is very high, say 10,000 Hz, 50,000 Hz, the number of cycles repeated is very high. An AC cycle is repeated 10,000 times, 50,000 times, then XC will be lesser and XL will be stronger. Now XL is greater than XC and this will be longer and this will be shorter. This voltage will be lesser. So you see, now you came to know that everything is decided or controlled by the frequency. How many number of cycles are repeated in this AC? That is the important factor now. Okay, but what to do, sir? At what frequency this circuit is? When you construct a circuit and connect a source, that source may be supplying very high frequency in some cases, and number of cycles repeated in 1 second of AC is very high or maybe low. So what conclusion we can make? You can take any conclusion, no problem at all here, because even if you take the reverse conclusion, nothing will happen to your formula. How? I will tell you why it is so. Now let us assume that this frequency is very low. That means the number of cycles repeated are 10 Hz, 50 Hz, 25 Hz, something like that. Very less amount of cycles per second. When the frequency is less, XC is more, right? XL is less, so XC is greater than XL. Now this diagram holds good. If capacitive reactance is more and inductive reactance is less, then the voltage across capacitor will be more and voltage across inductor will be less. Then VC we have to have a longer arrow to represent the phasor, and VL we should have a shorter arrow to represent the phasor. Now if VC is greater than VL, in this case low frequency, we are not in this case, we are in this case. In such a case, what I can do? I can reduce Vc and Vl by subtracting them. Suppose this is 10 volt and this is 3 volt. 10 minus 3, I can write 7 somewhere here. Am I right? I can write this as Vc minus Vl. Do you agree? Right. Sir, suppose this is greater. If the frequency is very high, XL is equal to 2 pi nu L, that is very high, and inductive voltage is very high. Of course, the whole diagram will come here. It becomes VL minus VC. The answer will not change because you will move forward. Now, so we have concluded that Vc is greater than VL, and we have subtracted these two voltages, and now it is Vc minus VL. What about VR? VR is here. So finally we have to find out the voltage across the R and the total voltage across these two components, that is Vc minus VL. So voltage across these two components is Vc minus VL, and voltage across this component is VR. Find out the voltage across these two components. You can't add them, you can't subtract them, because they are having a phase difference of 90 degrees. This one as well as this one. Of course, you need not worry about current now. We have to worry about voltages only. So what you will do? Draw a parallel line here, complete a parallelogram. Does it look like a parallelogram? Yeah. You complete a parallelogram because you can apply the parallelogram law of forces. This becomes the resultant, and this is the final voltage. Do you agree now? This is the final voltage. And here is the current, here is the voltage. Remember, our final aim is, in this type of circuit, which leads and which lags, what is the phase difference, right? Here lies phi now. What is phi? Phase difference between current and voltage. Whether it is 90 degree current leading, 90 degree voltage leading, or whether they are in phase, that is what we have to discuss now. Let phi be the phase difference between the final voltage that we have applied, this one, and the current that is flowing, common current flowing through all the three components. So that is phi. Now find out what is V. Apply that parallelogram law of vector addition. So where should I write now? Shall I love this one? Because I have here this diagram we have to follow in the exam. The final voltage can be easily found out now. So you know that this is VR and this is Vc minus VR. These are the two things which you have to consider now. So you know that if you apply the parallelogram law, and one more thing, if you try to keep the peak values of voltages. Suppose if I want to write the peak values, this is the phasor which represents the RMS. Suppose this is the peak value of voltage, then I can write it like this. This length from here to here, I can represent it as this length as VRM, peak value of voltage across resistor. We can take all these as peak values, VRM, IM into R, right? If this is the maximum voltage, IM into R, VLM, IM into XL, VCM, IM into XC. Let us assume that all the voltages are highest, and highest value of current is flowing in the circuit. Then what is this one? This is VCM minus VLM, right? VCM minus VLM. Of course, I want to say many things in this, because in the diagram in the book we have Vc plus VL here. Vc plus in the sense vector addition. Okay, what about this one then? This length. Hope you have followed what I am doing. I have taken all these values as peak values now for the time being. VCM minus VLM. Okay, now this is what I want. Apply the Pythagoras theorem. This square plus this square is equal to hypotenuse square. So I can write it like this. V square is equal to, where do we have now? V square, this one, final voltage square is equal to hypotenuse square is equal to VRM square plus VCM minus VLM whole square. This square plus this square is equal to the resultant voltage square, hypotenuse. What is V is equal to? V is equal to square root of course I can write it here only, V is equal to square root of VRM square plus VCM minus VLM whole square. V is equal to square root of, now substitute, what is VRM? The maximum voltage across resistor is maximum current into resistance. IM into R whole square plus IM into XC, voltage across capacitor maximum, voltage across inductor maximum Im into XL whole square. V is equal to, shall I rub this now? The total voltage across all the three components is, you see, root of Im square into R square plus Im square, I can take it outside, Xc minus XL whole square. Of course, this formula is also important. This gives the total voltage across all the three components. Now, Im can be taken outside. Im square common. Outside the square root. Im, of course, this voltage is the peak voltage, right? Vm, I can write it as Vm. The total maximum voltage applied across all the three components. Im into square root of R square plus Xc minus XL whole square. Bring this Im here, right? Vm by Im is equal to root of R square plus Xc minus XL whole square. And what is this Vm by Im? That is the total voltage across all the three components from here to here, right? VR, Vc, VL all together, that is Vm. Of course, even all the values are peak values, Vcm, VLm, and Im is the peak value of current, common current that is flowing through all the three components, and Vm by Im can be written as the total resistance, isn't it? Total voltage divided by total current. Is it not the total resistance? But we don't call it as resistance because there is a resistor of resistance R. There are two components, inductor and capacitor, which have reactance also. This is the combination of resistance, reactance and reactance. I call this as Z, that is called impedance. It is the total impedance. Total voltage by total current is called impedance of the circuit, Z. So finding it out is very easy. First of all, find out the voltage. So you may be asked to work out problems to find out the total voltage across all the three components by giving individual voltages, and then you have to use this formula. You may be asked to find out what is the total impedance of the circuit. You see, we got resistance, ohms. Inductor and capacitor gave some resistance to the flow of alternating current. We call it as reactance. But when we connected resistance, capacitor and inductor all together series, we had resistance, reactance, reactance. Totally when you calculated it, it is impedance. But remember, impedance is not equal to R plus XL plus XC. You see, we got another problem here, right? Total voltage is not equal to Vrm plus VLm plus VCm. It is not equal to the addition of the voltages. Total voltage is equal to square root of Vrm square, voltage across the resistor square, plus Vcm minus VLm whole square. Again, I come back. Sir, suppose voltage across capacitor was less, voltage across inductor was more. We kept it as it is that. If this is more and this is less, what would have happened is, the whole equation would have turned into VL minus VC, VLm minus VCm, but there was no problem because when you square it, even that negative becomes positive. Even if you take it as VCm minus VLm or VLm minus VCm, answer is same because you have a square here. It doesn't produce any minus or plus here. It is always plus here. Whatever you take on the other way. So no problem now. Whether the frequency is less or frequency is more. For low frequency, XL less, XC more. For high frequency, XC more, XL less. Whatever it is, answer is same. So this gives the total voltage and this is called impedance of the circuit. We will discuss it once again in the next class. My video is waiting for the last few seconds. So thanks for watching the class. We will meet in the next class again with the same discussion and we will continue it further. Thank you.